All right, welcome back again, everybody. Today we're going to continue our discussion about graphing trigonometric functions. In particular, we're going to graph some transformations of these functions, including vertical stretches and horizontal compression stretches, phase shifts, vertical shifts, all that stuff. But this is a really important skill that you're going to need forevermore, so I wanted to have a whole section dedicated to it. We'll also take a look at some examples on Desmos and so on. Honestly, this section is chock full of examples. So yeah, hang in there. All right, let's get the slides up and let's get going. All right, so we're on section 6.6, only talking about transformations of the trig functions. And here's the overview. I'm going to start with a little bit of an introduction. We're going to parse things out in different ways. We're going to talk about vertical displacement, vertical scaling and reflection, excuse me, horizontal scaling and reflection and how that affects the period of these functions. Then we're going to talk about phase shifts. And then the bulk of the lesson is going to be dedicated to graphing trigonometric functions using key points. You're going to have to be able to sketch these functions by hand throughout the calculus sequence. So I want to give you a comprehensive and clear and intuitive way of doing it that you'll be able to carry with you easily when you get to those courses. Okay. So, excuse me. Um, Now that we have an idea of what the standard trigonometric functions look like, the graphs, we're going to do transformations. Well, I guess this is the good news. The transformations, the properties of those transformations are identical to what we talked about back in chapter 2, when we looked at transforming arbitrary functions. It's the same now. No real difference except graphing them by hand, the trig functions. It helps if we take note of where those key points are. It makes it easier. Transformations of the sine and cosine functions specifically are called sinusoidal functions, and they have this general form. Hold on one second. There we go. Clear my throat. Um, yeah, so sinusoidal functions are functions that have this general form right here. A times sine of omega x minus phi plus b. So those are sinusoidal functions. All right. Um, we'll do vertical displacement first. So remember when you add a quantity or subtract a quantity to the output of a function that gives you a vertical shift? Same thing happens here. So we're going to let b be a real number and think about the function sine of x plus b, for example. That the graph of that is just going to be the graph of sine shifted vertically by b units. Same thing we saw in the past, except now it's the sine function. Yeah, that's pretty much it. Now, the horizontal line y equals b is what we call the midline of the graph of a trigonometric function. It's kind of the line that the trig function hovers around. So it's called the midline. All right. So let's try this now. Let's see. Do I want you to try this one? Man, there's so many examples here. Uh, I'll do this one first. Okay. So let's graph one period of this function, y equals sine of x plus 2. Surprise, surprise. It's just going to be the graph of sine, which we saw in the previous section, shifted up by 2 units, and that's it. So here, the midline was y equals 0. So when there is no vertical shift, the midline is 0. But when there is a vertical shift, the midline is going to be that vertical shift. So it's going to be at the point, or sorry, at the line y equals 2. But the graph looks the same. It just kind of hovers around that midline. It's just shifted a little bit. Okay, maybe you can try this one. Okay, so I'll start you off early. I want you to try to graph one period of the function y equals cosecant of x minus 1. All right, think about that for a minute. All right, and now is the time to verbalize it, say something out loud. Anything to get the juices flowing, get your brain thinking. Maybe cosecant is the reciprocal of what function? Try to say that out loud. All right. And now try to graph it yourself. Remember the tip that I gave you in the previous section was if you want to graph the reciprocal function, try graphing the non-reciprocal function first, and then use that important property of limits to graph the reciprocal function. So you try that on your own, and we'll do it together in a minute. All right. Now let's do it together. So Cosecant is the reciprocal of sine. So we want to graph the sine function. And what we're going to do is we're going to graph the sine function and then shift it by one, downward by one. And then we're going to use that important property of limits to get the cosecant function. So here we go. Let me zoom in actually so I can show you this. Let me go to the zoomable slides. All right. So again, first thing you do when you want to graph the reciprocal function is you would graph the non-reciprocal one. Then you use that property of limits to get these, right? So same thing here, except what we're going to do is we're going to draw the transformed non-reciprocal function first. That's what's going on right here, right? You can see it. So I took the sine function. It's kind of hard to read right there. Maybe I'll fix that. But we shifted the sine function down by 1 unit. Now the midline is right there. It's at y equals -1. And that midline is where we're going to look at our zeros and our asymptotes and things, right? So everywhere that sine crosses that midline, we're going to have a vertical asymptote for cosecant. And then that's pretty much it. Then you can just go like that and like that. And that is the shifted version of cosecant. All right, so that's the idea. Do this. There we go. Okay. Now let's talk about vertical scaling and reflection. Same thing as we saw before. If you multiply the output of a function by some number, it's going to result in a vertical scaling. It'll result in a reflection if that number is negative. So if a is a real number, then the function a sine of x will be the graph of sine of x scaled vertically by a factor of a. If a is negative, it's going to reflect it across the x-axis, right? Now, another nice thing about this is remember that sine of x is bounded in size. So sine of x is between -1 and 1. Same with cosine of x. So when we scale these functions, the resulting functions are going to go between -a and a. So basically, a sine of x is less than or equal to, I'm sorry, the absolute value of a sine x is less than or equal to the absolute value of a. So in this case, when we're taking that sine function or cosine function, we're going to stretch it. Now the graph is going to go between -a and +a. That's what will happen in this case. Now, if there's a vertical shift, that'll affect that as well. We'll get to that in just a minute. So try to graph this one here. I'll leave you to do this one as well. Try to graph one period of the function y equals 2 times cosine of x. All right? Think about it for a sec. Okay, now verbalize something. Maybe what key points can you use to graph it? And now try to work it out, and we'll do it together in a moment. All right, here we go. Okay, so it's the cosine function, so it roughly looks like that, but it's going to be stretched by a factor of 2. The midline is still going to be y equals 0. There's no vertical shifting or anything going on, but now the highest point that cosine will achieve is 2. Right? Because when cosine is at its maximum, it's equal to 1. Now we're going to take that value 1 and multiply it by 2. And then when cosine is at its minimum, it's usually -1, but now we're going to multiply -1 by 2 to get -2. So here's what we've got. Here's the graph of cosine, and now we're just going to take it and stretch it. So now it goes up 2 and then down to -2 and then up to 2 again. Notice the zeros don't change position at all, right? That's because 0 times 2 is still 0. So those are still there. All we've done is stretched this thing like so, just a stretch. All right. Now we need to talk about something called amplitude, and that's related to that a value. So the amplitude of a sinusoidal function is is the distance from the maximum or minimum value to the midline. So maybe back on this picture, I'll zoom in for a minute. The amplitude, oops, there we go. Ah, hold on. There we go. Hey, come back, come back. There we go. The amplitude is this distance, or for this distance right here, from the midline to the maximum, or from the midline to the minimum. That is what we call the amplitude of the sinusoidal function. There we go. Okay, yes. So if our sinusoidal functions are written in this general form, then the amplitude is the value, absolute value of A. It's the distance from the midline to the peak or the trough. Here's an important note. So technically speaking, the other trig functions don't have an amplitude, quote unquote, because they don't have a minimum or a maximum value, right? Tangent is unbounded, for example. Tangent goes from negative infinity to infinity. Even cosecant and secant, they're not bounded. Their ranges go to plus and minus infinity one way or another. So they don't technically have an amplitude. However, that value of A is still going to give us a vertical scaling factor. So we still need to take note of it. It's just technically, it's not the amplitude at that point. All right. Okay. So just to kind of summarize things, again, this is really the same thing that we saw before. Even the link that I have here on Desmos is the same link that's in those slides from chapter 2. But just looking at stretches or compressions of these graphs, if A is negative, the graph gets flipped about the x-axis. If the size of A is greater than 1, you get a vertical stretch. If the size of A is between 0 and 1, you get a compression. So if you want, you can follow that link there, and we'll take a look at this Desmos example right now. All right. So same thing we saw way back when we were talking about transformations. Here is a general sinusoidal function. In this case, I'm using the sine function. And what I'm going to do is just change the value of A. Now this is going to make a lot more sense since we like know about these graphs. As A gets larger, you get that vertical stretch, right? Just stretching it. The zeros don't change place. If the size of A is less than 1 but greater than 0, it's crushing it down, right? If A is negative, you get that reflection, vertical reflection. Boom, 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 just like that. All right. So that's the basic idea. Let me put this back to 1 for now. Okay. All right. Now let's talk about horizontal scaling and reflection and how this affects the period. So this is one of the reasons why it's actually easier to see how the horizontal scaling is going to affect the graph. Because with sinusoidal functions, you can really see how it affects it. And there's a really good intuition for why and how this effect is working. So you remember the formula for angular velocity of an object in circular motion? We talked about it back in section 6.2. Omega equals theta over t. And this is basically the change in the angle versus time, right? How much the angle is changing. It's like the speed of the angle changing, right? Where theta is the angle swept out and t is the time traveled. Now, this formula immediately gives you an equivalent formulation just by multiplying both sides by t. And it's that. It says that theta equals omega times t. So if you think about if you think about theta as the input of our sine function or cosine function or any trig function, really what omega is doing is it's speeding up or slowing down the circular rotation, the circular motion, right? So this means that the faster or slower the object moves in a circle, the faster or slower the angle changes. So this thing is like encoding the velocity of the rotation, right? Just like that. Now, because of that, omega is going to affect the period of the graphs of our trigonometric functions. So if omega is a really big number, right? If omega is large, then that means the object is going woo, 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 really, really fast. And if the object's going really, really fast, then that means both the horizontal displacement and the vertical displacement is going really, really fast. And that means that our graphs are going to get squished, right? Our graphs are going to get squished. So if the angular speed is very large, then the period of the resulting function is going to shrink in size, because it's going around really, really fast. And yeah, that results in a horizontal scaling. So if omega is a real number and we think about like sine of omega x, that's going to affect the horizontal behavior of that graph. This actually holds true for the other 5 trig functions, not just sine. So let's take a look at that in this case. If omega is negative, you're going to get a horizontal reflection. If the size of omega is 1, you get a compression going really, 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 really fast. Compression. If the size of omega is between 0 and 1, now the object is moving slower, slower. slowly going around. And so that makes the period stretch. All right, so omega affects the period. Let's take a look at Desmos one more time. So now what I'm going to do is I'm going to alter B in this case. B in the slides is omega. So B, if I increase the size of B, it compresses the graph because the object is now flying around the circle really, 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 really fast. And so the period is shrunk. The period is much shorter, meaning the graph repeats more frequently, right? The graph is going, zoop, there's a full revolution, zoop, there's a full revolution, zoop, there's a full revolution. That's what happens when omega is large in size. If it's between 0 and 1, right? Here's omega equals 1. This is the standard the standard sine curve. You can see here's 2 pi, pi, 0. This is pi over 2, 3 pi over 2. But now if I make omega smaller than 1, things get stretched out, right? Things get stretched out. So notice here, if omega is half, like zero point 0.5, check this out. Look, this is now 2 pi. It's literally like only half the period has occurred in this amount of time, right? So we only went halfway around the circle. I'm sorry, the object traveled halfway around the circle, but very slowly. So now we're here, right? We're here. And the period has now doubled in length. If you want to go all the way around the circle, then you've got to go all the way around very slowly. That's the thing. So it's getting stretched. That's where you're getting compression versus stretching. Okay, let me set that back to 1. Bink. Okay, let's go back to the slides. All right. This is pretty much what I was saying before, so I won't repeat it. Uh, just what I was saying. If the size of omega is large, you're going to be rotating faster. Now let's talk about phase shifts. Okay, so if you remember, subtracting a value from the input of a function before you evaluate the function gives you a horizontal shift, right? It's shifting the graph to the left or the right, depending on the sign plus or minus of this number phi right here. Oh, that's the Greek letter phi, spelled Phi and pronounced phi. Also, if you multiply the input by some scalar, you get a horizontal compression or a stretching. And if you do both of these things, both will occur. Now, we talked about this back in section, I think it was like 2.4 or 2.5, when you had both of these, both a horizontal scaling and a horizontal shift. So that can happen here as well. So suppose omega is positive just for convenience, and we're going to look at what happens with this kind of a sinusoidal function. Now, sine of x minus phi is a shift of the graph sine of x by phi units. But sine of omega x minus phi is a shift of the graph of sine of x horizontally by phi over omega units. All right, so there's a little subtlety there. But what's happening is the scalar omega is affecting the shift because the shift value phi, it's being applied to omega x, not just x, just like we talked about back in section, it was 2.3, there you go. Yeah, this phi is being subtracted from omega x, and we're not plotting omega x on the x-axis, right? This is the x-axis, not the omega x-axis. So shifting omega x by phi units is the same as shifting x by phi over omega units, and then scaling by omega. This equation kind of shows it. If you factor omega out of both of these terms, then this becomes x, and this becomes phi over omega. So that's why the shift in this case is phi over omega and not just phi. All right. In the event that omega is equal to 1, then this just becomes this, and then this just becomes this. Like it just becomes phi at that point. Okay, so what is this shift called? This is what we call a phase shift. And I'll give you some motivation, some intuition for why, some knowledge on the mathematical horizon. So if you've got a trigonometric function in just a general form, the phase shift of the function is the value phi over omega. And this holds true for any of the trig functions, sine, cosine, tangent, their reciprocals, but it's called a phase shift. And what I want to do is I want to give you a little glimpse into something you will study in your major courses or just in more detail in the future. Like, why is it called a phase shift? What's the meaning of that word phase? And the classic example is the spring example when you're studying simple harmonic motion. All right, simple harmonic motion. So let me pull up this animation. You can follow that link as well. So this is the spring example. And one of the reasons mathematics is so awesome and so powerful is it lets you encode things that you're witnessing in real life mathematically, and then you have all the tools of mathematics to explore that. And then you can retranslate what you learned mathematically back into reality and see what that means. So this is an example of an application of trigonometry, specifically simple harmonic motion. So this is the spring example. Pretend you've got an object suspended from a spring and it's just bouncing up and down, right? Let's assume that it just keeps going forever. So we're going to do a very toy example here. It's bouncing up and down, bouncing up and down. Well, you can relate the position of this object and its velocity using, well, the big picture. The big picture right there. Oh, it's funny. The mouse even got large when I did that. So this is an application of trigonometry here. And this plane is what's called the phase space. All right, it's the phase space. So notice the green dot, that's basically the point moving around the circle. But that motion, that rotational motion, can encode this vertical change, this vertical motion right here. So on the y-axis, the position is encoded, the position of this object. And then on the x-axis, the velocity is encoded. It's like the speed, right? So check this out. Down, up, down, up, down, up, down, up, right? So that's what's going on with the y-axis. Now let's look at the x-axis. The x-axis is actually encoding the velocity or the speed, right? So notice that when the object hits the bottom, its speed becomes zero. It has to like stop and then it goes back up. And then when it goes back up, it stops again. So if you think about what's going on uh, in terms of the speed, it's being plotted horizontally. And every time that green dot crosses the y-axis, that's when x equals zero. So the velocity is zero, right? Okay, stops, 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 stops. X is zero, X is zero, X is zero, X is zero. So this is a situation where um, this motion is being plotted in terms of the orbit of this point, where the position and the velocity are plotted in the phase space. This is what you'll use this kind of stuff for. That's why it's so important. And a phase shift just means, well, you're starting this point somewhere else along the circle instead of at zero or at the midline, for example. That's all it is. If you've got a phase shift, then you're not starting at the midline of the motion, you're starting somewhere else. Maybe you're starting at the peak or the trough or anywhere in between. That's why it's called a phase shift. Okay. All right. So stuff for you to ponder and make sense of. Although I should have I should have done this. Wait, I can't resist. I got to do this at least once. Got to do this at least once. Hopefully that was a little bit mind-blowing for you. I always think it's mind-blowing. Okay. Now, what was I saying? Back to the slides. Okay, here we go. Um, So that's why it's called a phase shift. And if you're uncomfortable just reading it off as phi over omega, then what you can do is you can actually factor omega out of both of those terms, excuse me, and you can rewrite the function like so, just like we did back in chapter 2, okay? Now you can visibly see the phase shift, just like so. Now, why is this important? Well, if we have a phase shift, then that is going to affect our key points. The phase shift will affect where those key points lie. And that's what we're going to talk about now. So the rest of this lesson is dedicated to graphing these functions using key points. I've got a slew of examples. We're going to do a bunch of examples in the activity. You'll have practice on the homework, and you're going to get to do it a lot more later as well. So If we want to sketch these functions by hand, we use key points like we did in the previous section, right? These are the points that normally occur at the quadrantal angles or at the standard angles more generally. Those angles like 0, pi over 3, pi over 4, pi over 6, pi over 2, 3 pi over 4, 3 pi over 2, all those. Those are like standard angles. And each one of those standard angles gives us a key point. Now, the key points are affected by the transformations that are applied to the functions. The key points are going to correspond to maxima, minima, zeros, or asymptotes of the function. And we're going to see how in the next minute here. Okay, so we've got a couple of propositions. Just a little bit of fair warning, this might feel like information overload, so I do apologize for that, but don't worry yet. Just take a deep breath and let out any of that anxiety. We're going to make sense of it. And you don't need to memorize these propositions. What you'll find is that when we do a few examples, the process becomes pretty clear. You just got to remember a couple of little details. So here's the first couple details, and we'll see them at play in the examples. For these trigonometric functions, sine, cosine, cosecant, secant, the period of those functions is 2 pi over omega. All right, 2 pi over omega for the functions that ordinarily have a period of 2 pi. For the trigonometric functions tangent and cotangent, the period is pi over omega. And that's just because the period of tangent and cotangent is pi. That's the basic idea. So when it comes to the period of these transformations, it's 2 pi over omega or pi over omega. And this makes sense because this is just the standard periods being scaled by a factor of 1 over omega. All right. There's another important quantity that's called the rotational frequency of a trigonometric function, and it's just the reciprocal of the period. So if you've ever heard that word frequency in the context of, radio or anything like that, it literally means the reciprocal of the period. So the period is how long it takes for the thing to repeat. The rotational frequency is just the reciprocal of that. And what the frequency is, it's just how many periods occur in unit time. Often measured using hertz. It's often measured in hertz. Oops, there should be a D right there. So if you've heard of hertz before, that's what it's measuring. It's measuring how many cycles are occurring in 1 second, for example. Okay, now, like I said, this is where it feels like information overload. Don't worry, don't fret. When you're graphing everything except the tangent function, the key points will lie at these x coordinates. Again, we're going to see this in action in a minute. So if you want to know where your key points are, meaning the quadrantal angles, like where they get moved to, it's going to be phi over omega plus 0 times the period divided by 4, and then plus 1 times the period divided by 4, 2 times the period divided by 4, 3 times the period divided by 4, and 4 times the period divided by 4. And we're going to see why in just a minute. Now, if you are instead graphing a transformation of the tangent function, the counters here are going to be a little bit different. The phase shift still affects everything. But now, instead of this going 0, 1, 2, 3, 4, it's going to go -2, -1, 0, 1, 2. Okay? That's the difference there. So for everything except tangent, it's going to be 0, 1, 2, 3, 4. But when it's tangent, it's -2, -1, 0, 1, 2. I'll explain why right now. So first of all, dividing the period by 4 splits the period into 4 equal-sized pieces, and that's going to be at the quadrantal angles. Then you're just going to count how many pieces you have. Appeal to counting. Make your life easy. So the multipliers for these p over 4s, these things right here, the reason that they differ for tangent is because the initial branch of tangent is symmetric about the origin, right? That's why it's -2, -1, 0, 1, 2. Because remember, the tangent graph looks kind of like this, right? Where that's the x-axis and that's the y-axis. So that's why the counters are going -2, -1, 0, 1, 2. Whereas for the other graphs, the counters start at 0, 0, 1, 2, 3, 4. That's it. That's the only reason. If there's a phase shift, that'll affect the location of the key points. And in particular, the key points will be shifted by exactly that amount, exactly that phase shift. Okay, so here's kind of a rough template. If you want to graph one period of a trigonometric function, you follow these steps. And we're going to do, man, a bunch of examples in just a second here. First, identify the relevant trigonometric parent function. Is it sine? Is it cosine? Is it tangent? Remember, if you want to graph something like secant or cosecant, then you're going to think that the parent function is going to be cosine or sine, right? Then, once you know what parent function you're working with, you're going to determine A and the amplitude if available. You're going to find the midline and the period. So just by looking at that formula, you're going to say, okay, what's A? What's the absolute value of A? What's the midline? What's the period? Write all that information down. Once you have that information, you're going to take the period and divide it by 4. Okay, and that p over 4 number is what you're going to be counting to get your key points. Zero of that, 0 times p over 4, 1 times p over 4, 2 times p over 4, 3 times p over 4, 4 times p over 4, or negative 2 times p over 4, negative 1 times p over 4, 0 times p over 4, 1 times p over 4, 2 times p over 4. That's what's going to happen here. Then you find the phase shift. Remember, the phase shift is phi over omega. So you find the phase shift, and the key points are going to occur at multiples of p over 4 shifted by the phase shift. Done. Okay, now let's do it. Let's practice it. I'm going to do a couple examples on my own, and then I'll have you do, wait, which one? No, I'll do the first one. You can do the second one. Then I'll do one, and then you can do another. We'll kind of bounce back and forth and trade off. So let me do this one first. So the first one says graph this function using key points, and we're going to use that guideline, that list to help guide us. So first, the relevant parent function is sine. So roughly speaking, the graph is going to look like this. The sine function, right? It starts at 0, goes up, goes down, goes back to 0. What is A? A in this case is 3. So the amplitude is the absolute value of that, which is 3 again. Then we need to find the period. So in this case, omega is 4. Omega equals 4. So we're going to take the period of sine, which is 2 pi, and we're going to divide it by 4. 2 pi over 4 is pi over 2. So now we have the period of our function. The midline is 0. There is no vertical shift. So it's going to be around the midline. Now we divide the period by 4. So we take this number, we divide it by 4, and we get pi over 8. Now we have pretty much everything we need. The key points, there's no phase shift, right? Our phase shift is 0. So our key points are going to be 0, 1 times pi over 8, 2 times pi over 8, 3 times pi over 8, 4 times pi over 8. That's it. Those are going to be the x coordinates of those key points. Now let's graph it. Here we go. Graph the midline. Okay. And what you do is you basically start at the end and you call that your period. In this case, the period is, what was it? It was, forgot it, pi over 2. Okay. So this right here, this is pi over 2. Then you're going to cut that interval into 4 equal sized pieces. So, like so. Right? 1, 2, 3, 4 equal sized pieces. And then at each one of those marks that you made, that's going to be a key point. So there's this one, pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. That's it. Now, what is the amplitude? We found the amplitude to be 3. So we're going to go up 3 units from the midline, and that'll be the maximum, and down 3 units from the midline, and that'll be the minimum. Then we're going to plot all of our key points. Here's the first one, second one, third one, fourth one, fifth one. And then once they're plotted, connect them with a nice smooth curve, just like that. That's how you do it. Okay, now you try. Okay, I want you to try this one. So look at it for a minute, think about it for a minute. Okay, now say something out loud about it, maybe just some details you notice, maybe the amplitude, maybe omega, something like that. Anything to get your brain thinking about it. Okay. Now work it out on your own, okay? You can go through that list. What's the relevant parent function? What's the amplitude? What's the midline? What's the period? P over 4, what's the phase shift? And then key points. Okay. All right, now let's do it together. So I can see this stuff just by looking at it. For one, it's cosine, so it's going to look roughly like that. The amplitude is going to be 2. There's no vertical shift, so the midline is 0. The period is going to be affected. The period is going to be 2 pi divided by 1/3, which is going to be 6 pi, right? And that makes sense because here omega is less than 1 in size, so we're getting a horizontal stretch, all right? Then I can divide 6 pi by 4, and so on and so on. Rather than say it out loud, let's look at it. So cosine, A is -2, amplitude is 2, period is 6 pi, like I was saying. The midline is 0. Dividing p, the period, by 4 gives us 6 pi over 4, which is 3 pi over 2. Again, there's no phase shift, right? There's no phase shift. So our key points are going to be at 0 times 3 pi over 2, 1 times 3 pi over 2, 2 times 3 pi over 2, 3 times 3 pi over 2, 4 times 3 pi over 2. Okay, almost done. There's one last detail here, and it's this. Notice that A is negative, right? A is negative. So because A is negative, we're going to get a vertical reflection. So normally cosine would look like that. Now it's going to look like this. Our graph is going to look flipped. So that's what it should be. Here we go. Now, how do we do this? Here's how I always recommend doing it. Oops, come here. There we go. So first, oops, um, basically start at 0 and then plot somewhere out here that's going to be the end of the period right there. In this case, our period was what, 6 pi, I think? Is that right? Yeah, 6 pi. Then you're going to cut that interval into 4 equal-sized pieces. Cut it in half, and then cut each of those halves in half. Those are where your key points are going to lie. And they're going to be exactly these numbers down here. There it is. So I'm going to write them all out. So 0 times, oops, 0 times 3 pi over 2, 1 times 3 pi over 2, 2 times 3 pi over 2, 3 times 3 pi over 2, 4 times 3 pi over 2. And then what's our amplitude? Our amplitude was 2, so we're going to move up 2 from that midline and down 2 from that midline, just like that. And then plot all the key points. 1, 2, 3, 4, 5, and connect them with a smooth curve, and that's it. Now, another note I want to make here that some of you might be thinking, this will vary depending on the instructor, but for me, these key points right here, I would rather you just leave them unsimplified. You do not need to simplify these in my class. Other classes, they might require you to simplify it. I don't. I actually would prefer it if you did not simplify these things because simplifying them actually hides the structure of that location, hides the structure of the point. Remember, we talked earlier in the course about how sometimes simplifying makes things harder to understand and it kind of obfuscates the information. I want to see this information. I want to see that you know what P over 4 is, and I want to see you counting in P over 4s. Okay, so that's my class. If you're taking my section of this course, I would prefer it if you left those unsimplified, but you do have to label them. You do have to label them. You can't leave them unlabeled, but you don't need to simplify it. Like you don't need to write this as 3 pi and this as 9 pi over 2. You don't even need to write this as 6 pi if you don't want to. I would rather you leave them unsimplified. Okay. All right, now let's do one that's a little more challenging. So now we have a phase shift. We also have a vertical shift. So I'll do this one, and then you can do the one next after this, okay? We're going to do the same process. So I'll say it verbally, and then I'll go through. Parent function is sine. Um, parent function is sine. The amplitude is 3. The a value is 3. There's a vertical shift, so the midline is going to be different. The midline is going to be at y equals 1. Omega is 2, so that's going to affect our period. 2 pi over 2 is pi. And then now we're going to have a phase shift. So that's going to affect our key points. Let's take a look together. This is almost everything I just said except for the phase shift. Amplitude, period is 2 pi over 2, which is pi. Parent function is sine. Midline is y equals 1. Now, what is the phase shift? Remember, the phase shift is phi over omega. So it's phi over omega, which is pi over 2. So all of our key points are going to be shifted by pi over 2. If there was no phase shift, it would start at 0. But now that there is a phase shift, it's going to start at whatever that phase shift is, pi over 2. There we go. Okay, let's write our key points. To do that, we need to take the period and divide it by 4. So we're going to take pi and divide it by 4, which gives us pi over 4. And then here are our key points, right? We're doing sine, so the key points are going to be phase shift plus 0 pi over 4, phase shift plus 1 pi over 4, phase shift plus 2 pi over 4, phase shift plus 3 pi over 4, phase shift plus 4 pi over 4. And now we have all the information we need. So let's graph it. Here we go. Okay, now we have a phase shift in this case, so we're not going to start at 0. We're not starting at 0. Our first point is going to be at the phase shift. So right here, pi over 2. Then go some distance out. Go some distance out, and that's going to be the end of the period. Now, cut that interval into 4 equal-sized pieces. Cut it in half. Actually, let me do this there so I can see those numbers. Cut it in half. Cut each of those in half. And now you know the x coordinates of your key points. You can label them. These ones I actually did simplify. Pi over 2, what was it? Pi over 2, yeah, pi over 4. 1 plus pi over 4, 2 plus pi over 4, I'm sorry, pi over 2, plus 1 pi over 4, pi over 2 plus 2 pi over 4, and so on. Okay? Now the midline. Remember, there's a midline involved, and the midline is y equals 1, so we got to shift everything up by 1. And then we have our amplitude. Our amplitude is 3. So we need to go to that midline and move up and down by 3 units. Up 3, down 3. And now we plot all of our points. Here's 1, 2, 3, 4, 5. And there's the graph. Maybe another note that I'll make here, you might notice that these graphs are looking very similar. That's okay, because they are just transformations of the parent function. In this case, it's sine, right? The key to this is labeling, okay? Like I said earlier, whenever you make a graph, you've got to label, label, label. Include the labels, label the axes, label the units, right? You don't need to put every single tick mark. You don't need to put every single tick label, but you have to label it. The idea with a graph, any graph you make, is that a person should be able to look at your graph and derive the formula for that function, okay? They should be able to derive the formula for that function. This is a sinusoidal graph. Looking at the graph, I can tell everything I need to know. 3 pi over 2 minus pi over 2, that's pi. So the period is pi. If the period is pi, that means omega is going to be 2. Oh, there's a midline. The midline is 1. That means there's a vertical shift of 1. Okay, great. Oh, look, there's a phase shift. Pi over 2 is the phase shift, which means, again, omega is 2, and phi is going to be pi. There it is. Oh, the amplitude is 3, so there's a vertical scaling factor of 3. We can see all of that from just the picture. Okay. All right, I did that one. Now you try this one, okay? It's got all the same features, just a couple little details are different. So you think about this one. Think about it for a minute. Okay. Now say something out loud, just even something that you notice. What do you notice about the formula or the function? Okay. Now try to work it out on your own. You can fill in the notes on the slides. You can do all sorts of stuff. All right, now let's do it together. Bunch of stuff. I'm going to go to the slides just to save a little bit of time. The relevant parent function is cosine. A is -2. The amplitude is +2. Omega is pi, so the period is going to be 2 pi over pi, which is 2. Now, here's one catch. So be careful. The phase shift here is actually negative. It's negative, right? So this needs to be a negative number. In this case, this is, or sorry, this needs to be a negative sign. In this case, it's positive. So our phase shift is actually to the left. It's -1/pi, which is just -1/pi. There is a vertical shift of 1/2. So our midline is at y=1/2. And because a is negative, our graph is going to be an upside down cosine graph. Normally cosine looks like this. Now it's going to look like this. There we go. Now we know the period. We can find p/4. Period is 2. p/4 is 1/2. And now we're going to do the same thing we did before. Phase shift plus 0 1/2. Phase shift plus 1 1/2. Phase shift plus 2 halves. Phase shift plus 3 halves. Phase shift plus 4 halves. And that will let us graph the thing, right? So in this case, remember the phase shift is to the left. So we're not going to start at 0. We're not going to start over here. We got to start over here somewhere. So mark where you want to start your period, right over here. And then move to the right a little bit to mark the end of the period. And then divide that into 4 equal sized pieces. 1, 2, 3. There we go. Sketch the midline. There it is. You can label all of these key points right here. I didn't simplify them in this case. And then we know that it's cosine. We know that our amplitude is 2. And we know that it's a flipped cosine graph. So from 1/2 up to 2.5, and then from 1/2 down to -1.5, plot those points, and then connect them. All right, that's it. Okay, couple more examples. So at this point, I'll say you're welcome to pause the video and try to do any of these on your own. We're going to do a bunch of these in the activity as well. So don't feel compelled to have to do every single example on your own. I'm going to go through these on my own just to show you how to do them, but we've covered almost everything. We haven't done a tangent or a cotangent graph. We're going to do that after this example. But here, let's graph secant. So this one is negative secant pi times x plus 1 plus 1/2. So remember, secant is the reciprocal of cosine, right? The reciprocal of cosine. The good news is we actually already have a graph of this exact cosine function. That's what we did here, right? -2 cosine pi x plus 1 plus 1/2. -2 secant pi x plus 1 plus 1/2. And remember, anytime you want to graph the reciprocal of sine and cosine, you graph the original function first, and then use that important property of limits. So that's what I'm going to do right here. Yeah, we're just going to do this. So remember, our midline was 1/2, and then this was cosine right there. So to get our reciprocal function, everywhere that cosine crosses this midline, we're going to have a vertical asymptote by that important property of limits, right? And now we can sketch secant. There you go, just like so. And that is one period of that transformed secant function. That's it. So again, if you need to graph secant or cosecant, just pretend that it's cosine or sine first, graph that, and then just use that important property of limits, that reciprocal property of limits to get the reciprocal graph. Okay, now let's do tangent. We're going to do tangent and we're going to do cotangent. Same kind of deal here. We're going to use all the same properties. There's just a little bit of difference in the fact that the period is pi for tangent instead of 2 pi. So same deal. What's a? It's 2. The period is pi. This is omega, so we're going to do pi over 3. The phase shift is going to be 2 over 3. And the midline is at 1. Now, because it's tangent, remember the key points are going to be symmetric about well, I don't want to say the x of the y-axis. They're going to be symmetric around a0, I guess you could say, or not even a0. That's not quite accurate. They're going to go from -2 to 2 instead of from 0 to 4. I'll just say it that way. So we do p over 4 again. So we're still doing p over 4. The period is pi over 3. We divide that by 4. we get pi over 12. And then now this is what our key points are going to be. Phase shift minus 2 pi over 12. Phase shift minus 1 pi over 12. Phase shift plus 0 pi over 12. Phase shift plus 1 pi over 12. Phase shift plus 2 pi over 12. That's it. Now we can graph everything. Here we go. So we're going to plot our key points. Remember, our phase shift is positive, so we need to go to the right a little bit, just like we did before. Okay, we're going to go there. We're going to move out at some point to be the end of the period, cut that into 4 equal pieces. Cut, cut, cut. Now, at each one of those lines is going to be the x-coordinate of a key point. Then we're going to graph our midline, quote unquote. There we go. Yeah, yeah. I still call it the midline. Yeah, okay. All right. Now, what are our key points? Well, we're just going to look where those points from tangent would normally be and move them. So here is that center point. And then remember, tangent is going to swoop up like this and swoop down like this. We're going to have asymptotes at the end of the period. This is what used to be 0. So now it's going to lie right on the midline, right in between those asymptotes. And then this is going to be our next key point up here, our next key point down there, and then you connect with a smooth curve, like so. Okay, now one last example, cotangent. Cotangent. So again, same kind of deal, but remember with cotangent, the key points are still going to count as 0, 1, 2, 3, 4. It's only tangent where you have that symmetry, that -2 to 2 symmetry. All the other ones, it's 0, 1, 2, 3, 4. So same thing here. Here we go. A is 3. The period is pi over pi. In this case, omega is pi. So our period is 1. That's okay. In fact, it's very, very common to make the period 1. So that way the frequency is 1 and everything just works out nicely. It's like scaling everything so that it occurs in unit time. The phase shift is 1 over pi. And there's no shift, no vertical shift. So the midline is 0. What are our key points? Well, we take our period and divide it by 4. In this case, it's 1 divided by 4. And then now I really sound like a broken record. Sound like I'm saying the same thing. Uh, Phase shift plus 0, 1/4. Phase shift plus 1, 1/4. Phase shift plus 2, 1/4. Phase shift plus 3, 1/4. Phase shift plus 4, 1/4. And now we can graph. Okay, so our phase shift is right here. It's at 1 over pi. Mark that point, go out some distance to the right. That's going to be the end of the period. Cut that interval into 4 equal-sized pieces. Label your key points, or at least the x values. Here again, I didn't simplify. It's just, oh, I simplified like the 1/2 and things like that, but you don't need to simplify. You're just counting, starting at 1 over pi and then counting p over 4s. And then remember, cotangent comes down like this. So it's the same deal. Start at the center there. This is going to be up here. This is going to be down here. And then you connect them with a line like so. All right. Okay. Whew. On that note, let's play. Feels like we were already playing right there, right? A lot of information. We're going to do this in the activity, so don't worry if this was too much. No worries whatsoever. We'll be there to help. We'll help you do these. We're going to do a bunch of examples in the activity. You'll get some practice on the homework as well. But that's it for graphing these things. So yeah, I'll end it there. Thank you all again for watching. I hope you enjoyed it, and I will see you next time. Have a good one, everybody.